respect to what time. They are functions with respect to time. In electronics, you have periodic signals, sinusoidal signals. In waves, also, it's with respect to time. You have the angular velocity, the wave equation, the sinusoidal equation. So, good day, everyone. This is Chiamoji. Today, I'm going to bring to you the Laplace transform. There's one thing the society does that I don't like. Some of you just obey without asking questions. Sometimes you need to ask questions. First of all, there's this construct between, or comparison between, the Laplacian transform and the Fourier series. There's this comparison, but one thing is, Laplace transform has a great advantage because it can break down from one function into another function. Usually, Laplace transform is in the form of a periodic function. It is always with respect to time. There's a standard to Laplace transform, and the standard is like this: f of x, which is the function, equals to the integral with limit 0 to, this is the limit of integral, exponential minus st f of t dt. This is equation 1. Now you've seen this equation. Let's turn it so I can see it. So this is equation 1. So what happens here is that in the Laplace transform, it helps to break down tedious functions or high differential equations, breaking them down. And guess what? Laplace transform is also used in electronics when you have the input and the output. Whatever you put in, let's say this is the input and then this is the output. So now I'm going to break down everything for you. So this is the standard. If they ask you what is the standard, this is the standard. So there's another format. You can actually use it like this: f of x, f of the function x equals to small l, f of t, this is how it looks. This is equation 2. So if you don't understand equation 1, make sure that you understand equation 2, right? Where f of t is a function with respect to what time. They are functions with respect to time. In electronics, you have periodic signals, sinusoidal signals. In waves, also, it's with respect to time. You have the angular velocity, the wave equation, the sinusoidal equation. Those equations are periodic. That's where you have f of t. F of t. F of t can also be called wt, etc. Now, let's go back to this. Let's not waste time. Let's solve questions. For example, they say f of t equal to exponential at. So if they say solve this, that f of t is equal to exponential at, it's very simple. Just do your substitution. F of x equals to integral, this is the limit, integrating limit, exponential minus st, which is the standard. Then substitute everything here into here, exponential at dt. You can see that this is equation 2 because this one is supposed to be your first equation that you put. Then this becomes your equation 2. So what will you do further here? What you do further here is, since they have the same exponential, you have to say f of x equal to integral of, this is the integrating limit. You take one of their base, then bring it out. St and this. You can either put this before this or put this before this. But let's just bring minus, then s, then minus a, then t, dt. Why did I do it like this? I did it like this because minus times x is minus x, which is this. Then minus times a is plus a. Then we have the other one, s equals integral 0. Then if you take this like this, there's another format. So keep watching, guys. Keep watching. So now what do we do? Very simple, follow me. So at this point, what we have to do is to change this dt, change it into the u, so that we can further factorize it. Why? We don't want to see any t. The whole idea of Laplace transform is to transpose from the periodic function into a functional function, either the output or the input. We want to turn everything here to represent what is here. Do you understand? So we have to cancel this thing. Anything will be due to cancel this thing. And the best way to cancel this thing is to find what is here and then use this value, the integral limit, use it to find whatever is here. Now let me break it down for you. We call the whole of this thing. Let's call the whole of this thing u. U is equal to s minus a t, right? Then the u dt equals, if you can see it, s minus a, because when you differentiate this with respect to t will definitely go out. Substitute this back into the equation. If you substitute, you have f of x equal to the integral this and this exponential minus u, because everything here is now u, minus u, then dot the u is now 1 over s minus a. So doing it that way, what do we now have? We don't have the t anymore. Understand? We don't have the t. This is now the u. Everything here with respect to the u. So let us integrate with respect to u. If we do that integration, so if we integrate with respect to u, very simple. All we need to do is to first of all take this x minus a, take it out, then we do something like this. So integrating this, we integrate this with exponential minus, we substitute this into it. But if we want to put this back by saying we put what is here, u is ut, is the whole of this u, right? That's what u gave you. U is equal to s minus a, then t. Integrating it back, what we have there is s minus at. Okay, so this t, sorry, s minus a, then remember that this up is the first one, then raised to power infinity minus exponential minus, minus exponential minus x minus a 0. You put it, so this limit, we have succeeded in substituting them. This is this limit minus this limit. This is the lower limit, this is the upper limit. So we have f of x equals 1 over s minus a. What? It's raised to power infinity. This becomes 0 minus it's raised to power, this is raised to power 0. This becomes 1. So bringing it down, we have f of x equal to 1 over s minus a bracket minus 1 will definitely give you minus 1 over s minus a. So that's the function, and you can see that the answer is now in a function of x. So what am I saying? So what I'm trying to tell you is that the Laplace transform just helps you to transpose from the periodic function of any value. Even in engineering, we want to find this in the periodic function of this, then we take it to the whatever function we want, whatever variable that is our independence, we just transpose. So you see the answer. So